syncing the recording with, did we start?
Just started.
Excellent. I'm syncing by just making a transmission. All right, I hope that helps syncing. All right, let's start. We're going to discuss today automated methods for running our quantum calculations. We talked about lots of things in this workshop this week about RMG, about Arcane, about lots of different methods and aspects and exercises and examples. And I think this session will conclude or will give some conclusions to all of these and try to integrate everything we've seen into how would like the kinetics community to look like in the near future. First I'll say that it's not only our work or our views, there are different softwares in the community, and I'll mention some of them soon, that do exactly that. So some thoughts of automated model generation and refinement. This is a scheme that shows how we think model generation should look like soon, once we can automate things and we're on the right track, we think. So the user will give some input, just as you do for a regular RMG run, with just additional parameters that you can think of. For example, the level of theory you would like to run at. And there's a lot to say about that, but I won't go into all the details of what we think the input might look like. Then you run an RMG job, right? Maybe let's run it and not at the tightest tolerance because we'll have lots of uncertainties. Let's run it at a reasonable tolerance, get some model. And the next piece, before we go to automating calculations, is actually important. We'd like to transmit information from RMG to the automated calculator. Information such as the reaction family that we know from the 2D work, two-dimensional graph representation of molecules in RMG, we do know the reaction family of reactions we would like to calculate. And that's very valuable information so that the automated software won't have to just guess or run general methods. It will have more information about how the transition state might look like. And we can also think about running large data, many species and many reactions, so we might want to rank them and just have it on some supercomputer running all the time, but doing the more important things first. Important things means that species or reaction coefficients that we are sensitive to and we are uncertain of. Once we have that established, the next block is automating the quantum calculations, species thermodynamics and reaction rate coefficients. The first problem to solve is how a species might look in 3D. Again, RMG currently only thinks in 2D, which is all it really needs to. So we need to see how the conformer looks like. If you have lots of torsions in the molecule, you'll have a large search space for all the possible conformations. And which one is the most stable? Which one is the most likely for the molecule to really be? So first, that needs to be determined. And that's a global optimization task, and it's not easy. Then we need to actually run the calculations. So run optimization, local optimization at the level of theory you chose, single point energy, frequencies, Rodor scans, everything we really need to get all the statistical mechanics, information, and the partition function correctly for that species. Note that TS's transition states come after we have data for the species, and usually we'd like to first see that we got the species right. We have some suggestion for the conformers, so we can principally make a transition state out of that, and that's good practice if we do it manually and we don't want to wait. But if we automate, we want to make sure that we, for example, don't have a negative frequency for one of our species. If so, we'd like to troubleshoot it. So all that should also have troubleshooting methods. So in short, TS guesses will come after we have good optimizations for our species and frequencies, rotational scans, and everything that we know we have a good conformation. Then we'll need to come up with a guess for the transition state. That's a very challenging task. Once we do that, we have a possible TS conformation, but maybe not the lowest one. So maybe the reactive site, the reactive coordinates, we might got that correctly, but what about some other tails of the molecule that might rotate and bring us to a lower conformation of that transition state? So we should also look for that later. Eventually, after we have all that, from here it's kind of downhill, running statistical mechanics to get a partition function, running transition state theory to get high pressure limit rates, solving the master equation if you'd like to get pressure dependent rates. The next step, before we go back to RMG, let's wait a second. That reaction might be relevant or interesting for other projects as well. We just burnt valuable computational time. Let's save it in an online database which is accessible for everyone, open source to the community, so anyone can just manually log in, search for a species, search for a reaction, and get all the valuable information we just calculated, or automatically do that in that process. So maybe we should add another block here saying search for data in our database before you attempt to do all of that, all these calculations. So that's another thing to consider. Eventually we ask ourselves whether our model is good enough, whether we should terminate or not. If we had no calculations to do, so RMG terminated, that's great. If we have more information to feed into RMG's database and rerun the model, we'll do that. After we have established a good initial model, let's tighten our tolerance. So we'll get more species into the core and more reactions we care about, and let's calculate these, so on and so forth until we finally converge. Then, if we're doing automated things, let's automate the analysis as well. So we can get profiles. If in the input file we specify which observables you care about, that's easy, right? So let's automate that. Flux diagrams, sensitivities and uncertainties, they should really also be here in the selection criteria, but also reported at the end. Comparisons with our database. So if you calculated thermodynamics data for a new species which is not in our database, RMG has group additivity. So let's compare just to see we're in the ballpark and we haven't diverged too much. So if we have, let's flag it. Or for reactions as well. We had an estimate from RMG for that reaction. It might be off, but hopefully not too off. And if our calculation is in the ballpark, that's great. If not, let's flag that. How do we know if we're close or not? Maybe that's a user input. So these things haven't been established yet, but that's what we're looking at. Of course, making sure we have these nice visualizations for each species. So if the user would like to query a specific species or reaction, you can see the transition state, you can visualize it, and everything should be smooth for a user to just say, go, come back after a week, a month, I don't know, depends on the size of the model and the chemistry we're looking at, and then easily just visualize, see what might have gone wrong, what we would like to correct, and maybe think of ways to improve the model. What's presented here is pretty much what we already do, but it's a lot of work and it takes a lot of our time, and why not automate it if we can? And we can. So here we see the software behind the scenes that might help us do the tasks that we just presented. So for conformers, we use different algorithms that rig RDKit and OpenBubble, for example, that can help us generate some guesses. Still, it's a hard task to really get the global minimum of how the conformational structure of your species looks like. I'll elaborate about that when we see some examples. The quantum calculations, so we have a bunch of softwares, not only these of course, many softwares that we can choose from. For TS guesses, we can do general methods such as Groy string methods, nudge elastic band. We can also use existing tools like Kinbot developed in Sandia laboratories, which will give us excellent TS guesses for some of RMG's families. We can use AutoTST developed in Northeastern University in the Richard West's group that currently works great for H abstraction, and they're elaborating it for other reaction families as well. And for StatMech, we have all this software. Currently, we're using Arcane. There are many software developed in our community. Each one has its own pros. What I'll present today is Arc, and Arc is a fancy scheduler and troubleshooting method and tool that will automate all that process. Another project we have planned, currently all we have is a name and an idea behind it and some things we already prepared, but soon, hopefully this year, we'll start getting going on actually formalizing a database where we can save that information and which will be open and accessible to anyone, including bots that will do that for us. And then we need some high-level routine that will manage all that, RMG and Arc, and we know how to call each one in the database, which is a nice concert to manage. So I'd like to present Arc, a software developed by our group. It's just over a year old. We think Arc currently performs pretty good for thermal properties of species. We're still not claiming we have good rates, definitely not automatically, but we're on the way to go. We're on the way to establish that as well. The mission of Arc is to provide the community a tool, a well-documented tool for automatically calculating thermochemistry and reaction rate coefficients. I have to note, I want to note at this point, there are many tools in the community that also do that. If you'd like, we can mention them and discuss about each one's pros and cons. So it's not the only software that does that. I'll also note that we're collaborating with all the developers of other tools. We're not competitors or anything. Each one was created for different projects and has different properties. I would like eventually, I think we all would like eventually to have one standard in the community that does it and does it well. We're on the way to achieving that, and I hope it will be done. So what can I say about Arc, the automated rate calculator? Arc is a high-level module. It automates what we just discussed, the quantum calculations, and actually achieving thermodynamic properties and rates. I think it's flexible. I think it's modular. I will show that we can have a higher degree of modularity. It has an automated scheduler and quality assurance, so troubleshooting as well. I think it's organized and we have nice documentation. I'll show you later. We recently transitioned to Python 3. Originally it was written in Python 2, compatible with Python 3. It has already been run and tested in our group for several projects, so that was great for catching bugs. Definitely not bug-free, but we think it's pretty much robust. It has a nice restart feature, so if you run it and let's say if you run it on your local laptop and you need to shut it down, so you have a nice restart feature that will see which jobs are currently running on your server and will catch them and will see once they terminated, we'll look at their output files and parse that and see which other jobs it needs to spawn next. If you run it on a server, you should still be aware of the restart feature. You want to turn off the server, although that happens as well. If there's a very annoying tiny bug that crashes your software and crashes that procedure, and it's an easy fix or hard fix, whatever, you just fixed it, you'd like to restart and not lose all the calculations you already did. So the restart feature will help us do that. The input file is convenient. I'll show it soon. We're currently working on reactions, on getting TSs, and it accepts, it's very flexible in its inputs. You can just give it smiles, or you can just give it an RMG object, so a species object or a reaction object directly from RMG, so it's already prepared for the day when it's automated and connected intimately with RMG. Yeah.
Can you run it on a server that has like a job scheduler system as well?
Yes, absolutely. You can run Arc, and I'll show soon, either on a Slurm server or a OGE server. And you can do either, you can run it, let's say, on the head node, and it will just submit jobs to the scheduler, or you can submit that as a job by itself to a certain node, and it will spawn it will spawn jobs to additional nodes on the server. It can also spawn jobs from the server to other servers if you have your software installed there, absolutely. So it can be installed either locally or on a server. Arc has its own scheduler in a sense that it needs to know which job to spawn next. So first it will do conformers, right? Then optimization. Only then, once you have a good configuration, you'll do frequencies, and rotor scans, single point energy, etc. So we have our own scheduler in that sense, but we will use the server's scheduler just to organize the jobs, right? So here are two examples for Arc's input file. I'll say that you can either use the API or an input file. Of course, on the server you'll use an input file. In my examples, after the presentation, in the demo, I'll show the API, so in an IPython notebook, but they're both equivalent and they do the same thing. So here's a very simple input file. Just give a project name. It's important. You'll later make a folder with that name, so it should be a legal folder name as well. The level of theory you would like to use, flexible as well. Species you care about. So we have a label and we have smells, and you're done. Once you specify that, pretty much Arc will give you thermodata for these species. There are advanced features as well, and many additional things you can specify, and that's just a partial list. For example, you can give initial XYZ, you can set the job memory, whether you want to run orbitals, scan, don't scan, and we have defaults. So all of these have defaults. The defaults are meant for the primary user of Arc, which is none of us, which is RMG. So the defaults, we always ask, what would a tool that will spawn iteratively RMG in Arc, what would that expect? We do expect to run rotor scans, so that's true by default. For example, we have default levels of theory, so you don't have to specify them, but that's more in-depth input, and it's all documented. We'll see the documentation soon as well. What to expect after Arc is done. So here's the folder structure. As I showed you, the project name will become your project folder. Under that, you have two hierarchies. You have calcs, so the actual calculations, and some output. In calcs, you'll have species or reactions and TSS. Under species, you have labels, and then all the different jobs that ran with a unique ID. In output, first you'll have RMG libraries. So all the thermodata and kinetics is already spitted out in a form that you can just take, copy-paste into the RMG database and use. And it's ready and a legal RMG library that you can continue using. Then you'll have your species. So for example, I highlighted geometry. So these are the files under geometry. We have conformers. The conformers generated before DFT optimization, then after DFT optimization, if you care about it. I copied the frequency output file from the frequency calculation. It's been copied automatically. I think it's interesting for the user just to have that file. It's because you can visualize it, for example, in Gauss view or in Avogadro, and visualize imaginary frequencies or non-imaginary frequencies, which might be interesting. We have a figure of the geometry in some arbitrary point of view, so whatever that's worth. And then some files, a dummy Gaussian job file that you can open in Gauss view, and XYZ file that you can open in Avogadro or any other software with the optimized coordinates at whatever level of theory you're using. Arc kinda runs out of the box, so if you're using Arc Group's servers, the defaults are already great for you. All you need to do is just tell it, define the server, so give the server name, and then the actual address that you'll use, your actual username, and then your RSA SSH key. Once you have that, you're kinda alright to go and get started. Look at the documentation for all the instructions for how to install Arc. If you're not from our group, you'll have to modify your submit scripts as well. So here's an example. Currently, Arc supports Slurm and OGE or SunGrid Engine, SGE. Actually, we call it OGE. It was changed to Oracle recently, so although most people will call it SGE. You need to give it paths for the commands it needs to use on the server. So if you're not using OGE or Slurm, you need to modify that, and that's kind of easy to implement. And then you need to give submit scripts. For example, we have on Slurm submit scripts for Gaussian. Here it is, and we have keywords for Arc to complete for different jobs, like the job name, how many CPUs to use, etc. And then level theory. Oh, sorry. So that's a submit script, not the input file. We have the same thing. Anything else interesting? So pretty much your submit script that you already use, copy paste it and change the keywords that are important for Arc, like you will see in the examples. Arc has good troubleshooting algorithms, not amazing, not great. It can always be improved, and we're looking to get feedbacks from users if a job crashed. I mean, an electronic structure job crashed on your server and wasn't troubleshooted correctly. Bring it to our attention, and we'll see if we can debug it and add it to the automatic troubleshooter, so everyone can benefit from that. So it does some fancy things. I won't go into depth of everything we currently have for troubleshooting, unless you'd like to. Yes, please.
How many iterations do you typically do before you really decide this job doesn't
That we cannot. We will try everything that makes sense in troubleshooting, even switching software. So if you ran Gaussian and we try troubleshooting with all our keywords and couldn't, we'll try using QChem or something else. Usually it works great in reverse, right? I think Gaussian has a robust optimizer. If your level theory can only work in QChem, we'll try using Gaussian. We'll try using even CBS-QB3 because it's robust. Once we get the geometry, we'll plug it into the original level theory that you cared about, so we'll have a better guess than just the force field conformer. It's not always successful. And
when does it stop?
when does it stop? So it's not looping. It passes all the options that are feasible. We have conditions. We won't just apply all of them. And it stores for each job what it already tried. So once it exhausted everything that's reasonable to try, that applies for our case, it will stop and just declare the species cannot be troubleshooted.
For a particular reaction, is it one, or for particular structures, is it one sample guess at a time? Or would you spawn a few guesses, say for example you're looking for a hydrogen migration, you have a reasonable guess for what that transition structure might be, but you would say, if the program were aware of the reaction, you just move the hydrogen around a bit and then just submit, say, 3 guess transition state calculations.
Yes.
Allow Gaussian, for example, to run them individually, just wait until the feedback comes back and say, well,
Yeah.
that's the best one.
So the question was whether we spawn them let's say TSs simultaneously or not. Currently neither, because currently we're not we don't support auto transition state searches. The idea, so we do that for species, but if we talk about TSs, what we have in mind is for given reaction just to try everything we can, although it's expensive, and in parallel. So we'll do growing string method, nudge elastic band, and we'll see what Kinbot tells us, what AutoTST tells us, just everything we can do, because getting a TS is very challenging, and we'll try to hit it with all hammers simultaneously. Then we have several TSs. Some are correct, some aren't. So we'll run IRCs for all of them. Currently not implemented. then see which one is the lowest in energy, and IRC makes sense, and use that. Right. So it's nice to talk about it. We don't have code for that, but that's the idea.
But it sounds like you can generate a lot of data at the moment for types of reactions.
A lot of
At the moment, you seem to be generating a lot of data,
data.
and if you know what types of reactions they are, then you probably say, well, usually these types of reactions we can find out this way.
Yeah, yeah. So yeah, once you're more experienced, we can apply certain templates when we know the family. Right, absolutely. Yes.
For TS, instead of trying all the software, would it not be better just to, like, in the beginning, try all of them, but then like select, okay, this one has the highest success rate, so we first try this one. If that fails, we try the other one. I don't know. Just
Yes.
from a computational point of view.
Yeah. I don't know either. And what I think, so we can have success rates or known success rates. Let's say even for particular RNG families, right? It's valuable knowledge, and we can use that. And I don't have a clear answer. It could be something the user specifies in the input file. Use all hammers or use the recommended and default ones. Absolutely. But also, if we have success rates, what's a success rate? Successfully generating a guess or successfully generating the best one? And how do we know it's the best one if we don't run the others, right? And these are all like probabilities. So I don't know. I think it's going to be computationally intensive, no question about it. And I agree that we should allow the user to specify how much resources they have if they'd like to do that approach or something else. But again, currently it's just talking about these ideas, and I'd love to continue brainstorming. It's nice to talk about something that isn't implemented and say, yeah, we're going to do that.
Yeah.
We haven't. Yeah. Yeah, but yeah, these are all interesting questions that we eventually in the community we all need to solve, and to have just any user be able to run it automatically.
So that's a good question, because I know that some academics that don't have high allocations, sometimes they'll just run it on a server that they bought
Yeah.
just locally.
Yeah, just or on your laptop.
On your laptop,
And
yeah.
then you're dealing with someone who might have just a national allocation. And
Right.
you're like, well, let's just go.
Yes, absolutely. Absolutely depends on your resources, computational resources. What can we say? Yeah. Yeah. But what the alternative of doing it manually, so it's more work for us and same resources, right? So anyway, we need that, right? So lots of things to automate, but we said we also need a high-level supervising routing. And before I'll demonstrate Arc, I'd like to give a demonstration of our idea of doing that, and we have already done that. Here it is. We call it the Tandem RMG Arc model refinement tool, whatever. It's a branch on RMG. We haven't rebased it on the Python 3. It's kind of old, so not that old. Hopefully we'll be able to this year refine it better and be able to run it in tandem. So here's your input file. First you have your legacy RMG input file. All right, you have the RMG input file, and you have an additional Arc input file with some Arc directives. For example, level of theory and whatever you want for Arc. Then some additional directives, not all supported currently, but we're working towards that. What's currently supported is, do we have all species here? Principally, what that branch currently does, it looks at the source for the thermal data for all the species. If it's taken from group additivity, it will try to calculate it. That's what we do. What we would like to do is to be able to calculate the, let's say, 10 top sensitive, 10 top species that are observable is sensitive to. So you define the observable as well. Reactions, the same. Currently we were not supporting reactions. SAPDEP says that we might be sensitive to a pressure-dependent reaction, and let's look at the wells, at the isomers of that network, and see where that isomers were derived from. So we can recalculate a rate. That's great. Before we do the rate, let's recalculate the species inside the network and just pass them to RMG so it has better information when it regenerates that network. Collision violators. So we already output a file with collision violators. Let's calculate first the species. Everything we do here is just for species. Also SA reactions. Let's calculate the species in the sensitive reactions. We're currently not supporting auto transition states, so everything here is in the species context. Collision violators are reactions that violates the collision limit. Usually, not always, it's because some thermo is really screwed up and then the reverse rate got to be really high. So it doesn't make sense. We'd like to fix that. So we're not sensitive to it, but why have a reaction with a ridiculous rate that we know isn't physical? So we can fix that. We will be able to fix that as well. Alright, so let's see what that tool does. I'm showing here the log file after running RMG and ARC in tandem. So we start. Let's see, when did we do it? 2019 April, so like 6 months ago, not that long, it's not that old. So starting iteration 0 of the tandem tool. First, I added the logo, of course they won't appear in your log file. First it runs RMG, so you have the separate RMG log file. It will be in a different directory, iteration 0 RMG. Then once RMG terminated, here what did we do? Ethane pyrolysis at these conditions. So once RMG terminated, it took it just over a minute to do ethane pyrolysis. It says it has 16 species and 24 reactions in the core. But there are additional calculations required because what we defined as a criterion is whether we have species with group additivity values. The thermal library I used here, I should have mentioned, sorry, just gave us values for H, H2, methyl, and CH4, and bath gas, and that's it. Everything else will be calculated automatically at CC, SDT, F12 level. And these are the species to be calculated from the model, from the core, all of these. And the reason why we're calculating them, then it spawns ARC. So ARC, again, will have its own log file that you can later look at, but that's the tandem log file. And ARC took 15 or 16 minutes to calculate all of these at a very nice couple cluster level. All species thermodynamic calculations, it was fully converged. So everything converged. If not, it will tell us that some species did not converge. And it's very important for an automated tool because sometimes RMG will include non-realistic, non-physical species in the model, and we'd like to flag that and say, hey, if we really can't troubleshoot, either the species doesn't exist and RMG should know about it somehow, or we just couldn't get it right, and then the human might want to take a look. So iteration number 1, let's run RMG again with the created thermal library. I didn't say that this tool will take ARC's output, the thermal library just outputted, and will copy and paste it into RMG's database, and in the new iteration we'll just direct RMG to use that library. So now we have better thermal data in our library. So now we have a complete different model. It was also fast to generate. Now we have some C3s that matter that suddenly entered our core, so they will be run as well. Everything converged. Iteration number 2, and nothing else to calculate. We got pretty much the same model, 25 and 149, 24 and 148. So one species got removed from our core, probably because it had a high thermal than what RMG estimated. That's the summary of everything that got calculated, and it terminated in 35 minutes. It's a very small model, but we got pretty nice level thermal, and it was all hands-free, right? Just say go, and it went. So that's the refinement tool, still not merged, but we are in a good state, at least for combining RMG and ARC. And if there aren't any questions, we can maybe jump into the demo for ARC itself. All right, so just to sum up, first we separate the features we always incorporate into essentials and nice to haves. I think for species, for thermo, we're somewhere here in the good to have, or we have maybe diverged into the nice to have. So species are being taken care of. We're now focusing on reactions, and that's the summary. So let's jump into the demo. Feel free to interactively stop me and ask questions. Let's take a look. I'll start with something very courageous, running a live demo. I have some pre-run demos. I hope Murphy will be on our side and not on the other side. I ran it this morning. It took like 1.5 minutes, so it's kind of fast. Let's just run it and see what we have. So I'm importing arc and arc species to define them. Arc says first, the species I defined are water and H2S, so I think it's a nice comparison. I'll tell it which jobs to run, so optimization. Don't run a fine grid just because of the demo, let's make it fast. Frequencies, I don't need body association energies, single point, rotors. We don't have rotors here, by the way. I'm using a very sleazy level of theory, right? And I'm passing the species list, species 1 and 2. Arc will say hello, what git commit it's using. I didn't specify, for example, level of theory to compare our force field conformers, so it has its own defaults, it will use them, and so on. These are the species it will consider. So we have water, that's the geometry for water from the force field. We have H2S, right, interactive, so for large molecules it's really nice to see. Then here it is. So optimized at our sleazy method. So that's the final XYZ for water, and we have it right here. It also runs isomorphism checks. So let's say that the XYZ we optimized, if we perceive it into 2D graph, that it's exactly the same species we started with, and we haven't diverged into something else that we're going to run expensive calculations on, but don't mean to. All right, so I think it's done running frequencies, single point, and you see it's kind of fast because the species is fast, the species is slow. Then it gives us the thermodynamics from Arcane, just spits it out here, and it's saved in the log file just for humans to take a look, but also we have the RMG library that RMG can also read, so you don't need to copy paste anything. And then we have priority plots just for sanity, right? So RMG already has values. So here's the enthalpy determined by RMG. It could be an estimate, it could be the library. And here's what we just calculated at the level of theory we wanted. So you see, even our sleazy method, the resolution here is really large, right? So there are differences, but even that simple bit relief wasn't that bad, and same here for entropy. If you'd like to know where the data that RMG uses came from, it's important if we diverge from group additivity or diverge from our very well-calculated library, so you have that data as well. And then a simple report that what has converged, what hasn't converged, and total time it took it. So that was a successfully run live demo, everything went fine. Let's see some more interesting things. Yes?
What is the default you have for optimization and geometry and so
Yeah.
forth?
So the defaults are also something the user can easily change. We have a settings file, and it's all documented, and you put in your own defaults for all your jobs, and for specific jobs, you'll modify the input file or API for your levels of theory. The defaults I'm using now, I'll show you, I don't remember them all, that the default we recommend and the users start with are these. So for just conformers, just from force fields to see which conformer is the lowest, we'll use BitWeLeap with dispersion. For optimization, we're using Omega B97XD, Def2 triple zeta. For frequencies and scan, the same, should be the same, doesn't have to, but should be the same. Currently, I have BitWeLeap for single point, but the online version will say couple cluster F12 triple zeta.
And these you can run on all the software?
So it will identify which software is best to run it at. And you tell it exactly. And you tell it which software is available. Arc has a radar. You know what? Let me show you our radar. So in Arc Tools, will it be here? Determine. Is it, all right. If not here, then I. Sorry.
Is it the diagnostics?
Yeah. Was it there?
Yeah.
Yeah. Thanks. I think that might work as well. Determine. So diagnostics.
At the top.
All right. Thank you. Thanks, Max. So first, if you specify your servers in the settings, it will just search for softwares on your server. So it has a radar tool, and it will tell you which software you have. And you don't have to tell it which software to use. It can find out on its own. Found Gaussian on Ferros and so on. Trying RMG, tries all the servers I defined, and will eventually tell me what it found and a hierarchy of what it will use. But you as the user, and you should tell it which software you have, and that's like a dictionary. So you say, on server A, I have Gaussian, or I think it's by server. No, it's by software. Whatever, it's documented. So Gaussian, I have on server 1 and server 2, and then you give, and then it's organized. It's like in order. So it will try server 1 first. So you tell it which software to use. Then it has some conditions. If you give it a level theory, CCSDT, F12, it will know that F12 is only available on MolPro. Is that right? Right. So F12, it will only try MolPro. Otherwise, it will crash with a warning message, say, I don't have a software for that. So here it is. Using Gaussian, I have Ferros and RMG. QChem I have only on Ferros. Orca I have on these servers, and MolPro on these two. And it will go with Ferros first just because it tried it first. So it has ways to deduce which software to use, but you can also direct it and tell it which software to use. Yeah.
Also, let's say there's a small syntax difference between, let's say, how you define the DFT Gaussian versus
That's right.
QChem,
That's right.
there's a flag.
Yeah. So like Omega B97XD, or even more simple, MO6-2X. In QChem, there's a dash, MO6-2X. In Gaussian, it's MO6-2H, no 2S, no dash. So by that, it will also deduce which software to use. So that's it tries. So that's for software. Here's a larger demo that's not run live. It was pre-compiled. First, I show here different ways to define species, and there's an equivalent for an input file. So here you can see I can define a species by defining an RMG molecule object. That's the old version of defining from smiles. That's an old pre-compiled demo, if you can see the tiny differences. Currently we're not using that notation, I think. I can also just define an arc species. So here I defined an RMG species object, and I gave it a molecule. I can also just do it from smiles. Here I defined a species, an arc species. I give it label, I can give it XYZ, and I can give it smiles. I can just give one of them, either XYZ or smiles. Here I define an arc species by specifying, by not specifying XYZ, just smiles. You can also pass multiplicity and charge. There will be guessed, so trivial values for multiplicity. Charge will be assumed to be 0 unless you direct it otherwise. You can just pass an RMG molecule, so and you can use AdgeList, so pretty much it's flexible. Let's not worry about all that. So these are the species I will look at in this demo. So again, arc starts, these are the default levels actually we had back then. It changed a bit. It will identify waters automatically for our species, so we don't have large species, only one torsion for these 4 species, of course not for OH. It will run conformers for all the species and will compare them at DFT. And let's see what's interesting. We have the visualizations. At the end, we have our scans, so they were automatically generated and spawned here, and everything is also saved or in an organized way in your local folder, downloaded from the server. All right, loading are some RNG libraries. Just a second, and we have our parity plots for H and S, and it's done. That's it.
Before it does all of this, does it check the database if it actually did it already once?
No, so we don't check the ARMG database. We assume that if ARMG directed, so our user is ARMG, right? So we assume that ARMG requested to run it, that is, so it's not in the database. Checking the database is what we had in the presentation. Before we call ARC, some routine, so that our database doesn't exist, but once it does, some routine will check the online database, not ARMG's database, before we spawn ARC. So that's the essence. There are many other cool things to show. Let's see some reactions. So for reactions, as I said, for a transition state, you have to give XYZs. Actually, let's see that. I think that's a better example. All right. Here's a practical example of how to run rates in RMG, in ARC. I define my species, so in Python, right, just give a variable name, and I define the object, which is an ARC species. Just give a label and smile. So you can also give XYZ, you can also give multiplicity, and lots of other features. Look at the documentation. Here, for example, multiplicity isn't trivial, so I specified it. And I have my XYZ guess. Then I define an ARC reaction object.
How good does your guess need to be? Does it still go to molecular force fields?
No, so we don't do
Or
force
directly
fields.
to-
Yeah, we
Yeah.
dive directly to DFT.
So you need a pretty good guess.
Yeah, you need a pretty good guess, absolutely. Yeah. So when I define the reaction, I define a label where the reaction label corresponds to the labels of the species, and it will know to relate the reaction to the appropriate, to the corresponding species as well. And I give it a list of guesses, here just one, and it will just try its best to get the TS and get our rate as well. On the other demo, I used YAML files that Arcane saves. So if you run a thermo job in Arcane and specify structure, it will save a YAML file, which makes a lot of sense. If you'd like to take the outputs of Arcane and use them in a new Arcane run for, let's say, a rate now, or a network, or in ARC, or want to use it for on a different computer, when we gave the demonstration of Arcane, we saw that the input files, the species input file, for example, gives you paths to all the quantum job log files. But if you just move the machine, move the computer, or if you want to copy to a different folder, paths might break. So we have one file that just has all the StatMech information in a YAML format. So here I define an ARC species by just giving it a YAML file supported from Arcane. That it works great. It's not standardized in the community, and we're working towards that as well inside the database project that I briefly mentioned. Anyway, to make a long story short, you give it your species, it will identify the reaction, it also identifies the RMG family that corresponds to it, will run thermal for the species if it needs to. If it's from YAML, it won't run thermal, it already has it. It will compare thermal, and it also compares rates, as we see here. So the dashed line is ARC's calculation, and everything else are just libraries from RMG. The orange one and the green one are actually the same value, so they're overlap, and we can see a pretty good agreement with the best rate from RMG. It's great, but just remember, we gave it a TS guess, right? It will be even greater if it can do it on its own, hopefully so. And that's it. Some additional cool things we can tell ARC to do for us. yeah, here it is, right. Sometimes it's very useful to have bond dissociation energies for your project. Let's say you have a few molecules, you want to study that before you run your simulation. Let's see which bonds are easiest to break, what to expect. So you can just direct arc, not run thermokinetics, but just give you bond dissociation energies, which is nice. So here I do specify XYZ because when I come to specify bond dissociation energies and give it specific atoms, if it's just from SMILES, the atom labeling is random and I don't know which atom is number 1 and which atom is number 2. So I give it an XYZ guess, and that could be even a wrong conformation. If you tell it to run conformers as well, if it will find a better conformation, it will use that. But the order will be kept. The atom order is always kept throughout all representations. So even if I give a wrong conformation, but with the correct atom labelings, I can direct it to do bond dissociation energies for, let's say, atom number 1 and 2. So atom number 1 is nitrogen and 2 is carbon. Here I'm doing aniline. Here's aniline. So I want bond dissociation energies for all hydrogens and the carbon and nitrogen here. So that's how I defined it. In job types, I'll tell it, run conformers, maybe you'll find a better one. Not for aniline, it's kind of simple, right? But if it's a more complex molecule, it might find a better one. Frequencies and single point are important to get the energies, and 0 point energy correction, so we have good bond dissociation energies. The level of theory, you can also say which model chemistry to use in Arcane. If you remember, we said Arcane uses a model chemistry. And let's tell it to go. So that's our starting material. It will try to break all the hydrogens and that CN bond. So if you break the CN bond, you'll get NH2 and you'll get that benzyl radical, right? If you break the CN bond. And here it is where you just break all hydrogens, and all of that is just done for you. So it breaks all the hydrogens in the molecule, even from the nitrogen, as we can see here. Eventually, here it is, gives you a report. It's also available in just a separate file, just the BDE report. The latest version will even sort it for you from lowest to the most strong bond dissociation energy, highest. You can see the atoms and pivots. So it's nice to analyze a molecule and no work on your end. Just know how to define it, run it, and you get PDEs.
It does not account for the symmetry in the molecule?
No, we don't account for symmetries in the molecule when we do BDEs. No. We definitely could. No, we don't currently. So we repeat the calculation twice. All right. And last thing, so I have some additional tools opened, and they're all documented. If you have any questions, how we perceive molecules, or what else is available there, some visualizations and symmetries, we can look at that as well. So the last thing I'd like to show is how we get conformers. So here, for example, a drug molecule that we'd like to analyze. I'll jump to a different conclusion before I discuss that plot. I'll jump to that line which says that the hypothetical search space, if you take all rotation, all torsions into account, is 47,000, nearly 50,000 different conformations for that molecule. So first, it will try to take random guesses. So the number of guesses is automatically determined by the number of heavy atoms, the number of torsions, and in the version that will be merged soon, number of chiral sites as well. So we'll come up with some heuristics for how many random conformers to generate. You see, it's definitely not the entire search space, so we might not have the lowest one within the random conformers. We'll generate a map. We'll map all the torsions. So here we have pivots, and then we ask in all random conformers, these pivots, so that torsion, what values did it have? So all the green points you see overlapping almost are are just representing different conformers. So we have 1,000 green points here, but then we can capture the well. It's somewhere here. If it's not spread too much, we'll take a weighted average of it, so that's the red point, and say that's one of the wells for that portion. If we have a symmetric water, we won't consider the other wells. We'll just consider one of them. So here you can see a scan for that molecule. Some of them are very spreaded, so we'll take several sampling points for that well. Then what we'll try to do is take the lowest conformer we have from the random ones, which might not be, probably isn't the global minimum, and run it through the scan. So we'll take the lowest one and we'll make all the combinations that that map suggests to us. And here we have on the y-axis energies. What are the units here? I don't know. I think kilojoules per mole, also SI. If it's above a certain threshold, as you can see here, we will not consider these conformations. Otherwise, we'll just tweak all of them to eventually try to get to the lowest one, and we'll repeat it iteratively until we converge. The method works, but another challenge is how to really show that it works. So what do we compare to? We don't have a database of well-defined conformers for very large species to really see that we capture that well. And then eventually it shows you the structure. So if we take something simpler and run that, it should be fast. For small molecules, it will just be exhaustive. Below 1,000 combinations, it will just generate all of them and force field all of them and take the lowest one. So here's just a random species, and it will give us the conformer. That's not a great example because RMG has some problems reading it back from INGI. It's not reading it directly. RMG can represent that. But that's the idea here. So let me know if you have any questions regarding what we discussed before we wrap up. Alright, so we can wait for that briefly. Generating some conformers. Let's see, I think that's ibuprofen maybe. So while that goes, I can briefly show you some tools which are available online in our IPathO notebooks. I think they can be very useful for lots of research, even if you're not using ARC directly. So you might want to consider them. Here are the results for ibuprofen, and we nailed it. So the hypothetical number of combinations is low, so we just have the global minimum. We did an exhaustive search. Alright, so what do we have? That's again conformations. You can visualize quarter scans. We have a notebook for that. It's available in the ARC repository. You can just download that and run it. So ARC does it for you, Arcane does it for you, but if you just have the scan and just want to visualize it and see how it looks like, we have a script to do that, of course. Plot XYZ, so you can use, of course, Gauss view and Avogadro, but I think it's just easy and nice in your ecosystem of Python to just paste XYZ in whatever format. It could also be a file that will be parsed for you. Just give XYZ and it will visualize it for you. I just resized the screen, Firefox here, to 130%, so all the visualizations disappeared, but we can rerun it and quickly generate it again. Alright, so you can just visualize your XYZ, right? Nice. So you have sticks or just balls, and you can have a visualization of that. Also useful is perception. If you modified or tweaked XYZ in 3D and you'd like to see that it's the same molecule, or maybe it's something else, or you did IRC and you have products, you want to see what that is if you perceive it to graph again, or to smiles. So we'll use our perception algorithm, which was developed by Colin, so it's implemented in ARC as well, and we will perceive the graph representation from 3D. And another useful tool, if you're just running Arcane or any other software and you'd like to have automated external symmetries and optical isomer number, so we have a notebook for that. So here you see just different XYZs, and it will give us the external symmetry for something like that, and number of optical isomers. These algorithms aren't always perfect. We're currently or constantly working on improving them as well. Yeah.
So if you ignore Hilbert rotor because the barrier is too high,
Yeah.
do you account for that in your symmetry or optimizers?
So if I don't account for torsion because the barrier is high,
Yeah.
so do I account for it in my optical isomers? Why the optical isomer?
Not directly optical isomer, but if your barrier is too high, you
Yeah. So
basically have two molecules that you, and the other one you don't account for because you don't prove it.
all right. So now I
typically
understand.
what we do manually is change optical isomers or
Mhm.
something to, but I don't know, has ARC the way to account for that?
No, so the only thing ARC will do if the barrier is too high will invalidate the rotor, then we'll just treat that mode as frequency, right, as vibration. And we don't change the number of optical isomers here, but it's a good point. Yeah.
The
Let's.
small molecule that
yeah.
will not make a difference, but
Right.
I think for the drug ones,
Mhm.
you have a lot of,
Good point. I haven't thought about that. Thanks for bringing that up.
we can discuss that.
Yeah. Thanks.
But currently, enantiomer for Arcane is only 1 or 2, right? So if you have more than
Only what?
in the Arcane,
Yeah.
only acceptable enantiomer number is either 1 or 2. So if you have more than 3, let's say 2 invalid rotors, that means you have 4.
Yeah, it's like whether you have a chiral center or not.
Not necessarily,
Or more than
depends
one.
on your scan as well.
So I think, and I don't think they are accounting for all the enantiomers properly, kind of.
Yeah, definitely. I also think that's definitely something that we should open up and reconsider the way it's treated in all our packages. Right. So to sum up, there are still challenges, still many things to do, but here we have some steps we took and tools that will definitely help us do what we anyway do manually and try to speed up or make our work more efficient. And we also showed some preliminary results for rigging RNG and ARC together in a tandem tool, which is how we envision model generation and automatic model refinement will look like pretty soon. ARC is asking and open for contributions. If you have any ideas, any features, bring it up. The repository is would very much like to accept all developers, anyone who would love to be part of this project. We already have several group members here. You're most welcome to consider yourself as part of our team, brainstorm ideas, or contribute code and new features, and join us. Thank you very much, and let me know if you need, or let us know if you need help installing ARC, working with ARC. Any bugs you find, let us know. We'll quickly fix them or work on them together.